Welcome back to CS 111. In this lecture, we're going to learn about error handling with exceptions, and we're going to see how we can apply those techniques to a new type of data structure, the set. We'll learn a bit about sets in general, we'll talk about nodes, and then we'll go and implement a linked set. To get started, let's talk a little bit about how we can go and handle errors that occur on our computers. In the early days of computing, the hardware that our computer software ran on was very unreliable, and that was largely a limitation of the technology available at that time. Back in the 1940s and 1950s, things were largely still done with old school technology like vacuum tubes, a lot of manual wiring, and sometimes even electromechanical components like relays. These sorts of devices were much more prone to failure, either from the devices physically failing, like a vacuum tube going out, or from outside interference. The term bug that we use to go and describe a problem with a computer program actually originates from the Harvard Mark II computer, where a moth was found that had actually gotten into the system and had actually short-circuited some of the components. Thankfully, with modern integrated circuits, hardware failures have become very rare. We still see a lot of problems when we're going in working with our computers, though. One major cause is tied to poorly written software, either because we have code that was not written very well to begin with, or we have code that's not resilient in handling problems that might occur, like with the data that it's trying to process. Those sorts of scenarios can lead to programs going and crashing. Sometimes we also do see other causes from external devices, so things like going and working with hard drives or with scanners or printers. Those can sometimes cause problems. Or if we have software that is dependent upon network connections, like it needs to be internet enabled in order to go through and do its job. If there are problems with those network connections, that can also go and cause errors with our software. In terms of handling errors that do come up while our programs are running, the approaches that you can see used tend to vary depending on what language you're dealing with. Older procedural languages like C don't have great approaches normally for going and dealing with errors. If problems show up, sometimes it's hard to deal with them in a appropriate manner. But what normally happens when you're going through and using a procedural language is that we're going to go and communicate via return codes from methods to go and indicate if everything ran okay or if there was a problem. This might be a case of going and using a Boolean value like we had with the add method from our bag implementation that when indicated whether or not the item was successfully added to the bag. Or a lot of times what you'll see, especially with C used, is an int return code. And if a function goes and returns 0, that means everything is okay. If it's a non-zero value, normally that means something went wrong. And a lot of times you'll see tables in documentation for a program indicating what different return codes go and mean. So functions can have return codes, and then the program itself with its main function can also go and have a return code that can signify what went wrong. But, this is kind of a cryptic approach to things. Newer object-oriented languages like Java go and use exceptions to indicate when something went wrong. Exceptions are special objects that are designed to go and communicate details about the problem that occurred, a lot of times where the problem occurred in the execution of our program, and sometimes a user provided message or some other information that's helpful in debugging. I'm sure you've run into exceptions in Java before, and a really common one is if you're going through and using the scanner class to read user input. You can get, for example, what's shown on the screenshot here, where you go and have a case where the user types in something other than the type of input it was expecting. So it was expecting an integer, user typed in some text, it went and threw an input mismatch exception. By default in Java, if we don't go and do something specifically to catch that exception, it's going to end our program, and we'll normally see a stack trace like what's shown in red here. That's going to help us identify where the problem occurred in our code. In Java, exceptions can fall into two categories, checked and unchecked. Unchecked exceptions are of the classes that go and inherit from runtime exception. These are, generally speaking, your most common type of exception. And these are errors that are normally caused by problems with the data that you're working with or the way you're going and working with that data. These can be things like going and having a null pointer exception. If you go and try to call a method on a variable that you thought was an object but turns out to just be a null. Going through and having divide by 0 if you're trying to go and find an average. Things like that are caused by problems with your data. Unchecked exceptions are things that most of the time you can actually avoid having occur in the first place by some thoughtful coding and being smart about how you're going and programming things. Java does not require us to go and catch runtime exceptions, although it's generally a good practice to do that. If we don't go and catch a runtime exception, our program is just going to terminate with a stack trace. The other types of exceptions that we'll see in Java are checked exceptions, and these ones are most commonly related to file I/O. So like a file not found exception, for example. Java requires us to go and do something with checked exceptions. We either have to go and catch them in the method that goes and calls whatever method that might throw that exception, or we have to go and pass it up the chain, and we do that with a documentation note indicating that we might be throwing a checked exception. We do that by going and adding the throws keyword in the method header, and the method up the chain is going to have to deal with it instead. But if we don't go and either mark our method as throws to pass it up the chain or at some point actually go and catch it, our code's not going to compile. When a lot of programmers first learn about exceptions, they kind of go a little happy with going and throwing exceptions in their code. You know, if there's this case of something wasn't what we expected, I'm going to go and throw an exception. I would encourage you not to go overboard with exceptions, and the reason why has to do with processor instruction pipelining. So a modern processor is going to try to look at the instructions that are coming ahead to try to figure out what it might need to do so that it can get stuff ready. This goes in and helps improve performance. There's things like branch prediction, for example, that can go in and try to push this even further. The problem is that when we have an exception get thrown, any of this prep work that we did has to get thrown out the window. When an exception is thrown, our program is going to immediately stop what it's doing and going to go and shift over and instead run some code for going and handling that exception. And this can hurt performance, especially if a lot of exceptions are getting thrown in your code. It's good practice to go and handle exceptions so that your program still runs and so that the user doesn't go and get those nasty stack trace messages. But it's really better if you can just go and avoid having them happen in the first place, either by going and doing checks with like if statements, for example, to make sure that an object is not null before you go and try to work with it, or by going through and thinking about the cases in your own code where maybe instead of going and throwing an exception, you can just go and return false or do something else instead. The idea here is that you want to keep exceptions for things that are truly abnormal or exceptional conditions. They should not be something that is being triggered on a regular basis when your program runs. So when do you want to go and actually throw an exception in your program? Well, this is something that you'll get a better feel for more as you start to write code and write more code and see other people's code. But some thoughts here are that in general, when you have an abnormal condition that occurs that keeps your program from completing what it's supposed to do. Normally this is going to be something that's wrong, but ideally it's fixable. You can go and catch the exception and then go and correct from there and hopefully move on. When we're thinking about data structures in particular here, so things like bags, sets, and lists, and the other things that we're going to be learning this semester in 111 here, cases where you might see exceptions get thrown would be if we're going and working with invalid values, like going and trying to pass a null to go and store inside of a data structure, or if we go and try to perform operations that are just essentially impossible. We can't go and remove an item from an empty bag. Those might be examples of cases where you might see exceptions get thrown. When we attempt to deal with exceptions by going and catching them, we have to tell Java what type of exception we want to catch, and it'll go and catch an exception of that class or anything that goes and inherits from that class. I want to encourage you that when you go and start throwing exceptions on your own, try to choose an exception type that is going to be as specific as possible for your case. Don't go and throw just the base exception class, because that could be literally any problem at all. You want to go and try to find a type of exception that's going to better reflect the actual problem that occurred, because A, that's going to be a little bit more descriptive for you when you're trying to debug your code, because you'll see what type of exception was thrown. But B, also, it's going to give you better control when you're trying to go and catch exceptions, so that you can distinguish, hey, is this an exception that I actually know how to do something with that makes sense? Or is this something where, maybe my program is so far gone, I just need to go and allow it to terminate? Java includes a number of common exception types built into the Java language. Some of the ones that you'll see more frequently include null pointer exception. If you have an argument or just an object in general that is null and shouldn't be. So for example, if I go and pass a variable as an argument when I go and call a method, and it turns out that that variable's actually null and it shouldn't be null, I would want to go and throw a null pointer exception. Illegal argument exception is used for any other sort of invalid value when we go and call a method. So if I passed a null, I would throw a null pointer exception. If I went and, say, passed a negative number when the argument was supposed to be a positive number, I would want to go and throw an illegal argument exception. Illegal state exceptions are where you're trying to go and call a method and that method cannot go and be used at the present time. So for example, if we're trying to go and remove something from an empty bag that doesn't have anything to go and remove, that would be an illegal state exception. There is sort of kind of a little bit of a middle ground between, if I have a case where, say, I'm trying to go and remove a particular item and that item doesn't exist, should that be an illegal argument exception or an illegal state exception? I would lean towards going through and using illegal argument exception in that case, because the problem isn't really with the remove method as a whole, it's with the value you're trying to use with the remove method. For some data structures, we're going to have methods that are designed to go and take index numbers to go and retrieve values or go and set values. We'll see these especially when we get into lists. Index out of bounds exception, which is commonly used with arrays, also gets used in a lot of these cases here where we're going and passing a number that maybe isn't a valid index. Since exceptions are just classes in Java, we can actually go and inherit from an existing class like exception and go and create our own custom type of exception. This can be useful in some cases where you've got an issue that just none of the built-in exception types really adequately describe. Sometimes you might want to actually go and make your own custom exception there just because nothing else really fits. Going and creating your own custom exception can sometimes be useful if you're trying to go and collect additional data, like for debugging. You might want to go and create an exception class that has some additional fields where you can go and store more data to help you with the debugging process. In general, though, it's really best if you can just stick with the built-in Java exceptions. Sometimes you got to make your own, but if there's something that's already there that meets your needs, just go ahead and use it rather than going and confusing other people who might be looking at your code by going and creating a bunch of custom exception types. With that bit about exceptions out of the way, let's take a look at our next type of data structure, the set. Sets are very similar to the bags that we've looked at so far. They are a type of unordered data structure. The big difference between a bag and a set is that while a bag can store duplicate values, a set cannot. It's only going to go and store unique values. And that's actually a case where sometimes it can be useful. If you have, for example, data that you're going through and trying to find unique instances of, you might go and put it into a set, and that would go and filter out any duplicate values. In designing an interface for our set, it's going to end up being very similar to what we had with the bag. The one primary difference is that we can eliminate a count-of method because we can't have duplicate values. So at most, there can only be one of an item, and we can figure out if there is that already using the contains method. So this is the list of methods that we're going to include in our set interface. Our constructor won't actually be in the interface, but we'll do that when we have our class. We're going to have a method to go and add an item, one to go and remove an item where we specify the item that we want to remove, another version of remove that doesn't take any parameters. We'll have a clear method, one to find the size, one to find if our set is empty, another to find if it contains a particular item, and here I'm just doing a single method to go and retrieve all the items from the set as an array. I'm just doing a version of toArray that returns an object type array. I'm not doing the second method that we did with our bag implementation that went and accepted an array of a particular type and then returned an array of that same type. And the main reason for that is just simplification here. Now that we've learned a bit about exceptions, let's think about how we might want to apply them as we go and design our set interface. What sort of situations might lead to errors when we go and work with a set? Well, one case would be if we go and try to use a value of an incompatible type. So if I tried to go and store a string when my set was just taking an integer. This is a case where we don't actually have to do anything about it ourselves. This is going to be a compile time error because, assuming that we're using generics here, Java is going to see that a string is not the same thing as an integer, and it's going to cause an error when it goes to compile the code. So we don't have to actually go and write any code ourselves to go and deal with this. Another scenario that can come up would be if we were trying to go and add an invalid value of a compatible type. So say I was trying to go and add the value null, which is a legal value for an integer. Or maybe I want to go and have it set up so that my set can only take positive numbers, and I try to go and insert a negative number into my set. In this case here, it's really going to come down to how we want to define the operation of our set as to if we have to deal with this. If we want to say that the set can store anything, including nulls, then we don't actually have to do anything about this. We'll just go and store the values. If we do want to go and place restrictions on what we're able to go and store, then we're going to have to think about how we want to address this. This is going to be a runtime situation as opposed to a compile time one, and we're going to have to write some code that deal with this case. The next scenario that we might encounter is one that's going to be specific to a set, and that's if we go and attempt to add a duplicate value. This would be considered a runtime error because it's a problem that's going to show up when our program actually executes, not when it's compiled. There's two different approaches we could go and use for handling this situation here. One of them would be to go and rely on returning a Boolean value to indicate whether or not the item was successfully added. So we previously said that the add method was going to return a Boolean value, and that's what we did with our bag implementation. So if there was a case where the item could not be added, such as, for example, if it was a duplicate, we could go and return false. We could also think about going and throwing an exception. We could use illegal state exception, although actually I would suggest that if we went this route, we do illegal argument exception instead. In the case of an exception here, the reason why I'm suggesting the legal argument exception is that there's nothing wrong with adding items in general. The problem would be with the specific value that we were trying to go and add. The thing with going and dealing with exceptions is that it creates extra work for us when we go and actually store values, because we have to go and create a try-catch block to go and handle the case where we're actually attempting to add a duplicate value. So just from a usability standpoint, it might be better if we just stick with that Boolean value, that true-false. We're not necessarily going to be able to know why we couldn't add the value. So if we have a case where we have a fixed size array, it could be that we just ran out of space in our array. But for most cases, that's really going to just give us the information that we need. Was the item added or not? And if we go and eliminate the other potential cases of an item not being added, like if we went and used a linked implementation, or if we had a resizable array, then really the only thing that would come down to an item not being added would be because it was a duplicate value. Another case we could encounter is if we're trying to remove a value that doesn't exist. So this would be if I go and call remove and pass it an item that just isn't there in my set. This would also be a runtime error because it's something that we're not going to be able to detect at compile time. It's going to depend on what is actually in the set when our program runs. And like with our add example, we could handle this using a Boolean return value or by going and throwing an exception. As with the add case here, I would probably lean towards going and using the Boolean value to go and indicate that we couldn't remove an item because, again, it's just simpler for using the code here. I don't have to worry about dealing with potential exception being thrown and then having to create extra code to be able to go and try and catch that exception. The last major scenario that we can encounter when we're working with a set is if we try to remove something from a set that is empty. Like the other types of problems that we've been looking at, this is going to be a runtime error. This one is a little bit more complex in how we want to deal with it. With our bag implementation, and also with what we said we were going to do with the set here, we were having the version of remove that doesn't take a parameter go and return the actual object that it went and removed. We can go and do with the set like we did with the bag, and if there's nothing to be removed, we just go and return null. The problem becomes if we go and return null and we allowed nulls to be stored in the set, then we're going to have trouble determining if that null that we returned was because there was nothing there or because that was actually the item that was selected to be removed. So this is a case here where we might want to actually think about going and throwing an exception. And I would use the illegal state exception here, because in this case we can't run this version of remove at all if there's nothing there in the set. We do have to go and deal with the possibility that that exception is going to be thrown. We'll have to go and do a try-catch block, but this would actually give us the ability to distinguish if we're dealing with the legitimate data value null because that was what was removed, or if we're dealing with the null because of an error condition. So allowing us to have an exception here allows us to go and really understand what's happening in a way that we wouldn't be able to otherwise. And with the other cases, we can sort of come to that conclusion with the other version of remove and with add without having to explicitly throw that exception. Here, we kind of need the exception to be able to distinguish that. Let's go head over into Eclipse and we'll see how we can go and code up our set interface. Here in Eclipse, I've created a new project for us to use as we make our set interface. I'm going to start off by creating a package for our set interface. I'm going to right click on the source folder, go to New, Package. I'm going to follow the naming convention we've been using, edu.wvu.cs111. I'm going to call this set ADT, and I'll click Finish. Inside that package, I'm going to go ahead and make a new interface, and I'm going to call this set interface, and I'll click Finish as well. So I'm going to get this set interface file here. The first thing that I want to do is I'm going to go and add a generic type parameter of t here so that when we're working with our sets, we can specify what type of data we want to store. I'll also go ahead and add some JavaDoc for the interface. So this is an interface for representing sets, and I'll go ahead and put in my name as the author, and for the generic parameter t, that's going to be the type of data to store. Next, I want to go ahead and list the methods that our interface is going to require to be implemented. Going through what we had earlier, we have an add method with a Boolean return type, and that's going to accept an item of type t to go and add to our set. We'll have a void method called clear to get rid of the things that we have stored in our set. We'll have a contains method that returns a Boolean value indicating if the item of type t is present in the set. We'll have another Boolean method that's going to tell us if the set is empty. We'll have a method that goes and returns type t, and it goes and removes things from the set. We'll have another version of remove that is going to return a Boolean value indicating if the item was present and then removed from the set. So this is also going to be called remove, and it's going to take an item of type t. We'll have an int return type method called size to let us know what number of items we have stored in the set. And we're going to have our version of toArray that goes and returns an object array. Next, we want to add some JavaDoc for our methods. I went through and finished filling out the JavaDoc for each of those methods for the description of what the method does, the parameters it takes, and what it returns. The other thing that I want to do is go and document any of the exceptions that might be thrown when going and calling that method. That way, somebody who goes and makes use of the method will know that they might need to catch that exception. If this was a checked exception that we were going to go and list, we'd actually have to go and put a throws keyword to say, like if we had a file not found exception. But in our case here, we're not dealing with anything that is actually a checked exception. The exceptions that we said we wanted to throw, the null pointer exception and the illegal state exception, are both unchecked types. So we're good if we go and document them in our JavaDoc. The first method that we have that's going to throw an exception is the add method. So I'm going to go into its JavaDoc, and I'm going to add an @throws tag. And I want to list what type of exception might be thrown. In this case, we said that if somebody tried to go and pass a null value in to be stored, we were going to throw an exception on that. And convention in Java is that if you have a value that's null that shouldn't be, even if it's an argument, you go and throw null pointer exception. So after I go and list the type of exception, I want to list the situation where that exception might get thrown. So I'm going to say that it is thrown if item is null. If I go and hover over add here, you can see that I have this throws section that's shown here now. Because it's just normal text, it's going through and just kind of listing item like anything else here, even though I'm really referring to the item that is a parameter here. JavaDoc doesn't have a special tag to use for a parameter when you're embedding inside of a comment like this with throws, but the convention is to go and format the name of the parameter there, or variable in general, using the @code tag. So what I'm going to do here is I'm going to say it's thrown if, and then this @code tag goes inside of curly brackets, if @code item. So it's going to format whatever comes after the @code inside the curly brackets like it was source code. So if I go and hover over add now, you can see that it went and used a monospace font for item, which kind of makes it stand out a little bit here. We were also going to go and throw a null pointer exception from a couple other methods. So let's go and just copy and paste that into the JavaDoc for the other methods where it's needed. We'll put it in contains, and we're going to put it in the version of remove that takes the item we want to remove. The other case where we were going to throw an exception was with the version of remove that doesn't take a parameter. And we said that we were going to go and throw an illegal state exception if there was nothing that could be removed from the set. So for my comment here is I'm going to say that it is thrown if nothing can be removed from set. So now anytime anybody goes to implement these methods, they'll know that we've documented that these might be thrown, and anybody who goes and uses a class that goes and implements these methods, they'll know that they potentially need to handle these types of exceptions when they go and call the methods. Now that we have our set interface designed, I want to turn our attention to thinking about how we're going to actually implement the set, especially for our linked version that we're going to go and write here. So as we saw with a linked bag, when we have a linked representation, that means that we have a series of nodes that are chained together by going and using a field inside one of the nodes to go and point to the next node. When we did our linked bag implementation, we went and nested our node class inside a linked bag. And that made sense there because the node itself is really there to just support the internal operation of the bag. We're never actually going and exposing the nodes themselves to anybody outside of the bag's methods. The thing with that approach, though, is that I basically have to go and recreate that node class every time I need a new node. So what we're going to do now, instead of that, is we're going to create a reusable class that'll be a public class to go and represent nodes. This one's not going to be nested. It's going to stand on its own. And this will allow us to go and reuse it in multiple cases. We'll be able to use it here with our linked set implementation, but with other implementations down the line, we'll be able to go and use it there too. The class that we're going to implement right now is going to be what's known as singly linked, which means that we only have that link field going to the next node in the chain. Some types of data structures, especially linked list being the most notable example, can use doubly linked lists. And these ones are a case where a node has links to both the previous node and the next node. The advantage to this setup is you can go both forwards and backwards in the chain versus just being able to go forwards. Right now, though, we're just going to focus on a singly linked node. So let's head back into Eclipse and code this up. I've created this nodes project here in Eclipse. Under the source folder, I'm going to make a package for my nodes, and I'm going to go and name this one maybe a little bit differently than what we've been looking at so far. Kind of the naming convention when you're going and working with packages is that you use a singular name if you have a package that contains a bunch of disparate classes. Maybe they all go and are used, collectively to go and perform a task, like maybe going and managing a movie collection, but they're all kind of different things that they're going and representing. If you have a package that goes and contains a series of related classes, like what we have with singly linked node here, and at some point in the future we might have a doubly linked node class, that's where you tend to go and use a plural name. So that's why I'm choosing to name this as nodes, because this package then could go and contain a series of related classes with different representations of nodes. Go ahead and click Finish here. And in that package, I'm going to make a new class, and I'm going to call it singly linked node. And I'll tell it to finish. When we were working with our node class that was nested inside of the linked bag, it went and inherited the generic parameter from the parent linked bag class. Here, since we're not nested inside of anything, we're going to have to add our own generic parameter to this class. So I'm going to go ahead and add the tGeneric parameter. And then I'll provide some JavaDoc for the class. So this is a class to represent singly linked data nodes. Go ahead and specify author name, and our param t is the type of to be stored in the node. Our singly linked node class is going to have two fields in it, just like the node that we made with linked bag. We need to be able to store the data that we're trying to keep track of with this node, and then a link to the next node. I'm going to go and tag both of these fields as being protected, which means that anything inside of the same package, including this class, or anything that inherits from this class will be able to go and access this field, but nothing else outside of that. We did protect it when we had that nested node class, and there we were able to go and access the fields from the parent linked bag. Here we're not going to be able to see it from our linked set implementation because these are in different packages and the classes are not nested inside of each other. What we're actually going to do is we're going to create what are known as getter and setter methods to go and provide access to these fields. And we'll talk about why here in a moment. But let me go ahead and create some JavaDoc for my first field as the data is stored in the node. And then I'm going to have a protected field for the next node. And this one's going to be a singly linked node with the generic t parameter here. I want to make sure that I go and list that so that we get the data typed right. And I'm going to call it next node. And we'll do some JavaDoc for that as well. Next, let's take a look at the constructor here. I want to make sure that when somebody makes an instance of singly linked node, it actually has data to be stored inside of it. Going and requiring people to call a constructor that has a parameter for the data is going to make sure that there is actually a value provided for that. I'm going to add a second parameter as well that'll keep track of what the next node should be. If there isn't going to be a next node right now, it'll just be null. I could create two different versions of the constructor if I wanted. One that just had the data parameter and one that had both. But I'm just going to simplify things and have one. It's simple enough to just provide a value of null for that second parameter. If this was a language that supported optional parameters like C#, I'd actually probably just set that as an optional parameter. But I don't want to go to the trouble of actually coding up a second full-on constructor here in Java. My constructor is going to have to be public so that it's accessible from outside of the class. I need to be able to make new instances of this class. My constructor is going to be called singly linked node. I do not need to specify the generic inside of angle brackets here. I'm going to go and list the fields that I'm going to store the values for. And so I'll have a parameter t That's going to be our data. And we'll have another one that's going to be called next node. That'll be of type singly linked node with that T generic there. And we're saying that was going to be called next node. Inside the constructor, I'm just going to go ahead and store the values. So I'm going to say this.data, which is our field, is equal to data, the parameter. And we'll do the same thing with our next node. This.nextNode equals next node. And I'll go and provide some Java doc for the constructor. So we're going to create a new singly linked node. Data is the data to store in the node, and next node is the link to the next node. Getters and setters are special purpose methods that are designed to go and retrieve the value that's stored in a field, or to go and change the value that's stored in a field. The getter gets, the setter sets. There's a couple of reasons why we might want to go and use getter and setter methods for manipulating the values that are in a field, rather than directly going and exposing the field itself. One major reason why we might want to do this is if we want to have different levels of access to that field. When I go and tag a field as whatever access modifier I'm going to use, whether it be public or protected or something else, that same access modifier applies to both getting the current value of the variable and being able to change it. There might be cases, for example, where I want to allow the public, so basically anything outside the class, to be able to see what value is currently stored, but I don't want to allow everybody to be able to change the value. With the field, I can't control that. But by going and having separate getter and setter methods, I can, because I can actually put different access modifiers on each of those. So I could make the getter method be public, but the setter be protected or private or something else. Another case why you might want to think about using getter and setter methods is that they can give you more flexibility in what's being done with the data. If I'm working with times, for example, or time stamps, where I have a date and time, I might go and internally store that in a database using, say, UTC time, where it doesn't have any particular time zone offset. It's actually going through and saying that it's 0 time zone offset. It's essentially Greenwich Mean Time. But when I go and represent things for users, I might want to show it in their local time zone. So like Eastern Standard Time or Eastern Daylight Time. I can go and use the getter and setter methods to go and convert values. So when somebody goes and calls the get method, it takes the UTC time that's stored in the database and converts it to my local time zone and returns that. Or if somebody specifies a time in the local time zone, I'll convert it to UTC before I go and store it. With setters, we'll sometimes see them used to go and perform data validation to make sure that the values that we're trying to store are actually valid ones for whatever field we have. And another reason why we might want to use a getter or setter is just that sometime down the road, we think we might have a need for one of those features. Once you start having other code go and access the field directly, it's kind of a pain to have to go and swap out references for things if I decide I need to use a getter or setter down the line. It's a lot easier if I just go and set up that getter and setter from the beginning and just require any other code that interacts with my class to go and work through that getter and setter, rather than have them use the field and then me decide I want to restrict access to the field and use a getter and setter down the line, and then have to go and change out all this other code that's going and interacting with my field directly. Some other languages, like C# and Python, support something called a property. A property to the outside world looks like a field. It's something where you can just do dot the name of my property, and I can set that equal to something if I want to go and set it, or I can go and just go and take the value as input if I'm trying to get the current value. But when I'm going through and working with these properties, I can actually code up methods that'll be run when I go and get the value or go and try to set the value. Java doesn't support properties like that. Java is kind of old school with things. If we're going to have code that we want to write to be run on getting and setting, we've got to create separate methods for that. And the convention is we go and use the word get or set followed by the name of the field that we're trying to work with. Let's go ahead and code up getter and setter methods for our two fields here in the singly linked node class. Let's work with our data field first. Our getter method is going to have a public access modifier, and it's going to return type T since that's the type of our underlying data field. I'm going to call this get data, and it's not going to take any parameters. Normally getter methods do not take any parameters. Inside, I'm not doing any data processing to get the value ready. I'm just going to return what's stored in the data field directly. So I'm going to say return this dot data. For my setter, it's also going to have a public access modifier, and it's going to have a void return type. Normally void is what we use for setter methods. This method is going to be called set data, and it's going to need to take a parameter with the actual value that we're trying to store. So this should be of the type of whatever my field is, T, and I'm going to call it data since that's the name of my field. Sometimes you'll see people go and use val or value for this rather than going and using the name of the field. That's okay. Just be consistent would be my suggestion with that. There's no processing or validation that I need to do. I'm just going to store the value as is. So I'm going to say this dot data equals data. I want to go ahead and provide some JavaDoc for these methods. So we're going to get the data stored in the node, and we're going to return the stored value, and then we're going to go and set the data stored in the node, and our param data is the value to store. We also want to create getter and setter methods for our next node field. So let's do the getter here. It's going to be a public access modifier. It's going to return singly linked node with that T generic, and we're going to call it get next node with no parameters. And we're just going to go and return this dot next node. And then for the setter, we'll have a public void called set next node, and it's going to take a parameter of type singly linked node with the T generic that we'll call next node. And we're going to say this dot next node equals next node. And I'll go ahead and provide some JavaDoc for this as well. I'm going to create two additional methods here that'll serve us as kind of helper methods. The first one is going to tell us if the node that we're looking at is the last one in the chain, which basically means there is no node after it. This is going to be a public method, and it'll have a Boolean return type. I'm going to call it isLastNode. And all it's going to do is return the result of evaluating the expression this dot next node is equal to null. So if next node is null, that means that there's nothing else in the chain. We are the last node. So we're going to evaluate that expression and return the result. And just saying that this is going to return if this is the last node in the chain. It's going to return true if there is no next node. I'm also going to make a method that will go and swap the data value that's stored in this node with the data that's stored in another node. This is helpful for us if we're trying to go and reposition items, or in some cases when we're going and removing items. I'm going to make a public method here with a void return type. I'm going to call it swap data. This method is going to take a single parameter. It's going to be a singly linked node with the T generic parameter. I'm going to call that swap node. What we're going to do is swap the data field from this current node with the one that's in swap node. And to go and do that assignment, we're going to have three statements, and we're going to need a temp variable. So let's go ahead and store the data from this node in our temp variable. I'll say var original data equals this dot data. Then I'm ready to go and take this node and copy over the data from the swap node. So I'm going to say this.data equals swap node.data. And then finally, we're going to go ahead and store our original data in the swap node. So I'll say swap node.data equals original data. And we'll go ahead and write some Javadoc. So we're going to go and swap data stored in this node with another node. And our param swap node is the node to swap data with. So with that, we now have our singly linked node class created, and we'll be able to go and use it in our linked set implementation and also in other linked node-based implementations that we might write down the line. Like most of the other data structures, sets can be implemented using linked nodes or with arrays. We're going to focus on implementing them using linked nodes, specifically that singly linked node class that we just created. And this is going to go ahead and give us a set that will be able to store any number of items as long as we still have memory available to us. Let's go ahead into Eclipse and we'll see how we can code this up. Here in Eclipse, I've created this new linked set project, and I want to go and add my nodes and set interface projects to the build path for it so that I can make use of code from those other projects. In order to do that, I'm going to right click on linked set and go to properties. I'll go to Java build path, and I'm going to go to the projects tab. Here I'll go and click on class path because I'm not messing around with modules right now. I'm going to go ahead and tell it add. I just want to check the boxes for both of those other projects, and then I'll just tell it OK and apply and close. And that'll allow this project to go and work with classes that are defined in those other projects. I'm going to create a new package for our linked set implementation, and I'm going to call this edu.wvu.cs111.linkedset, all lowercase. Go ahead and finish that, and then we'll make a class inside of that. So I'm going to right click on the package, go to new class, and I'm going to call this class linked set, and down under interfaces I'll click add, and I'm going to search for set interface, and I'll tell it OK. I'll leave the box ticked here to go and create stubs for inherited abstract methods, but because of the generic parameter, it's not actually going to end up doing that automatically. I'll go ahead and click finish here, and you can see that I've got this new class created. Before we do anything else, let's go ahead and add the tgeneric parameter for our linked set class, and then I want to go and provide some Javadoc for it. So this is going to be a linked implementation of a set. Go ahead and specify the author name, and for the tgeneric parameter, that's the type of data to be stored in set. Right now we're getting a red squiggly line underneath linked set, and that's because I don't have implementations of the different methods that are specified in set interface. If I hover over it here, I'm going to tell it that I want to add unimplemented methods. So I'll get all these stubs here for the different methods that are coming from the interface. We're still going to have to code them up, but this will at least give us some space to start working with. Before I start working on filling out those stubs, I'm going to go ahead and create the fields that I need for my class. We're going to have two fields here, one for our head node and the other one to keep track of our size. For our head node field here, I'm going to make this be protected, and it's going to be of type singly linked node with the tgeneric. I'm going to call it head node. You'll notice I've got the squiggly line under singly linked node. That's because it hasn't been imported yet. So I'll use the quick fix here in Eclipse to go ahead and import that class, and then I'm going to go and add a protected int that I'll call size to keep track of our size, and I'll do some Javadoc for both of these fields. Here, when we start off creating our new set, we want to have the size initialized to 0 and head node initialized to null. Because those are the default values for those types, default for our reference type is null, default for an int is 0, I could actually forego having a constructor here. And this class would just use Java's default constructor, which doesn't take any parameters. It doesn't specially go and initialize any fields, but since the default values are okay, that works for us. I will go ahead and write a constructor though, just because when we get into more complex classes, I do normally like going through and including a constructor. That's kind of a personal preference thing there. My constructor here is going to be public, and I'm going to call it link set, and we don't need to have any parameters for this. All it's going to do is just go and initialize those two values. So we'll initialize head node to null, as there's nothing in the chain yet. So I'm going to say this.headNode equals null, and then I'm going to go and initialize our node counter to 0. So I'll say this.size equals 0, and I'll provide some JavaDoc. This is a constructor for a new set of linked nodes. Now we're ready to start implementing the methods that are coming from the interface. We'll start off with the add method. In my code here, I want to go and start off by handling cases that are going to result in us not adding items to the set. These are things where we can go quickly evaluate if they're going to occur and then just return right out of this method without having to bother with other code. The first circumstance I'm going to check is if item is null. And here I'm going to go and just write a simple if statement. I'm going to say if item is equal to null. What we're going to do is actually not return here. We're going to go and throw a null pointer exception. So we're going to throw a new null pointer exception. And for the message that I'm going to go ahead and pass here, I'm going to say item cannot be null. I don't, strictly speaking, have to go and provide a message when I'm going and creating the new instance of this exception, but it can be helpful there to give a little bit more description as to what the specific problem is. So if somebody tries to go and store a null, this is going to happen. We'll get thrown out of the method, and hopefully maybe something upstream went and will catch that exception. Otherwise, our program's going to terminate. Continuing on, we're going to go and deal with the case where the item already exists inside of our set. And here we said that we were just going to return false rather than throw an exception, although there's some cases where you might choose to use an exception instead. For this, I'm going to go and call the contains method to see if the item's already here. So if this dot contains the item that we're looking for, we're going to go and return false, which means that we could not add the item. Assuming that neither of those two if statements got us out of the method, that means that we're going to move forward with adding the item. What we'll do here is go and create a new node to start off. And what I'm going to do here is say var new node equals a new singly linked node with that t generic, and it's going to take two arguments. The first one's going to be the value that I'm trying to store, so that's going to be item. The second is going to be the pointer to the next node, and I'm going to go ahead and pass it whatever is stored as this dot head node. If there is already a node there for head node, that means that there's stuff in the set, and it's just going to become the second thing after this new head node that we're inserting. If this is the very first node that we're inserting, this dot head node will be equal to null, and we'll just go through and be setting the next node field to null, which means that this node is the last one in the chain. Once I have my new node created, I can go ahead and set my head node to be equal to that new node. So I'm going to say this.head node equals new node. I'll go ahead and increment my counter. So let's do this.size plus plus, and then we're going to assume at this point that the item was added OK. And we'll return true. Next, let's go ahead and take a look at the isEmpty method. So this one is going to return true if there is nothing in our set. And I can determine that two different ways. I can look at the size field to see if that's 0, or I can look at head node and see if that's null. I tend to prefer, in this sort of situation here, looking at head node to see if that's null, because that's also going to guard against me potentially having a null pointer exception if I have a method that's going to go through and check to see if things are isEmpty. In theory, both the size being equal to 0 and head node equaling null should only happen at the same time. If things are out of sync with the results they are going to give us in our test, we've goofed up someplace in our coding. So it shouldn't really matter which one I use, but I'm just going to go ahead and work with head node as my check. And for this, I'm going to go ahead and return the result of the expression that we go and evaluate. This.head node is equal to null. So if head node is null, this is going to evaluate to true, which will mean that our set is empty. Let's go ahead and tackle the version of remove that does not take any parameters now. The first thing that I'm going to do is figure out if we have an empty set. Because if there is, we said that we want to throw an illegal state exception. For my test here, I could go and use that isEmpty method, or I could look at size. But what I'm going to do is check directly to see if this.head node is equal to null. The reason why I'm going and doing things this way here is that I'm going to be using head node here and accessing some of the methods off of it in a couple lines of code here. So I want to make sure specifically that head node is not null, so I don't get a null pointer exception. And isEmpty is checking head node to see if it's null right now, but in theory that could be changed at some point down the line, so I'm not going to suppose that it always will be written the same way. I'm just going to go and check head node here myself to be extra safe. If head node is null, I'm going to go and throw a new illegal state exception, and I'm going to display the message that the set is empty. Assuming that we don't have an empty set, what we're going to do is remove the first item in our chain. So I'm going to say var removed node equals this.head node. Once I have gone and created this removed node variable, which will allow me to keep access to that head node, I'll be able to go and actually update the head node field to point at the second node. So I'm going to say this.head node equals remove node dot get next node. Notice here that I'm using the getter method. I want to go ahead and decrement the number of stored items. So I'll do this.size minus minus, and then I'm going to return the data that was stored in our removed node. So I'll return removed node dot get data. Let's go ahead and do the version of remove that takes the item that we're trying to remove. And here I'm going to start off by making sure that item is not null. I'm going to do an if statement here, but rather than checking to see if item is equal to null, I'm going to use one of the methods that are in the java.util.objects class. It's a static method. So what I'm going to say here is if java.util.objects, and I could actually go ahead and import that if I wanted to save myself some typing. But I'm going to say if that dot is null, and I'm going to check against item. So if isNull is true, then that means that item is equal to null. In this case here, I'm going to go ahead and throw a new null pointer exception with the message that item cannot be null. If we get past there, then we actually have a non-null item that we're going to be looking for. And what we're going to have to do is iterate over the nodes until we hopefully go and find the one that we're looking for. So I'm going to create this var current node, and I'm going to set it equal to this.head node. So we're going to start looking at the first node, and we're going to go and loop while two conditions are met. While current node is not null, which means current node is still a real live node, and while current node doesn't contain the value we're looking for. So I'm going to say exclamation point for not. I'll do current node dot get data, and for the data I'm going to go ahead and call the equals method on that and see if that's equal to item. If both of those conditions are true, so we have a current node as a real node, but it's not what we want, then what we're going to do is go and move on to the next node. So I'll say current node equals current node dot get next node. When we fall out of the loop, it means one of two things has happened. Either current node is null, which means that we've looked at all the nodes and we couldn't find the one we wanted, or it means that we actually found the node that we wanted, and that's what current node is going to be if current node is not null. So we'll write an if statement to check for that. So I'm going to say if current node is not null, then that means we found the item. And what we're going to go ahead and do here is we're going to go and swap some values around. It's going to be easiest if we go and just remove the head node and replace the value in current node with whatever was stored in the head node. I could use the swap data method that I created on our singly linked node class for this, but that actually creates a little bit more work than what we really need to do, because there's no point in me going and wasting time updating the node that I'm going to be deleting. What I'll do here is I'm just going to go and say that we're going to set current node's data to whatever is in the head node, and then we're going to get rid of the head node. So I'm going to say current node dot set data, and I'm going to set it to this dot head node dot get data. So we're getting the data for the head node, and we're going to store that in our current node. Once we have done that, we're going to go ahead and cut out the existing head node by updating the head node field to go and point at the one after it. So I'm going to say this dot head node equals this dot head node dot get next node. That's going to point at the second node. And then I want to go and decrement the number of items stored. So that'll be this dot size minus minus. And here in this case, we're done removing the thing, so we're going to go ahead and tell it to return true, to signify that we successfully removed it. I need to go ahead and add an else clause here, and this is going to handle where we could not locate the value. And for that, we're going to return false. For clear, I'm just going to have a loop that will just go and continually remove items while our set is not empty. So I'm going to say while not this dot is empty, then I'm going to go ahead and remove any one item by calling this dot remove and not specifying a parameter. So as long as there's something in the set, it's going to keep calling this dot remove. As soon as the set is empty, it's going to stop calling this dot remove. So that will prevent us from having our illegal state exception occurring, because that would occur when this is empty, and we're only going to go through and call that method when it's not empty. Our size method is going to be super simple. All we're going to do here is just return this dot size. For contains, what we're going to have to do is start at the beginning of our chain nodes and just look at each node until either we have found the item or we've exhausted all the nodes. Before we start searching though, I'm going to go and make sure that the item parameter is not null. And I'm actually going to use another one of the static methods from java.util.objects for this purpose here. So I'm going to use the one that is called require non-null. And it's going to go and take a parameter here with the item that we're trying to test, and then I can also do an optional message as a second parameter. So I'm going to say here item cannot be null. What's going to happen is if the item that we're actually going through and testing here is null, this is going to go and throw a null pointer exception, which is the same thing that we were doing manually ourselves. So this just does it in one line of code without us having to go and write an if statement. Saves a little bit of code, and if you've got a bunch of values that you're trying to test, this is going to look a little bit more cleaner and more compact in our code than having a whole series of if statements checking all the different possibilities. But once we're sure that we have an item that is not null, we're just going to go and iterate through our chain to look for the value. I'll create a var called current node, and I'm going to set that equal to our head node. And then while current node is not null, which means I have a live node that I'm looking at, I'm going to go ahead and see if it matches the one I want. So I'm going to nest an if statement inside of here, and I'm going to see if current node.getData equals item. If that evaluates to true, that means that we found our item, and we just want to return true in that case. That's going to go ahead and get us out of the loop. If we didn't find the item, then we're going to go ahead and advance down the chain to our next node. And we'll do that by saying current node equals current node.getNextNode. If we fall out of the loop without having returned already, that means that we looked at everything and we could not find what we wanted. So we're going to go ahead and return false. The final method that we need to code is toArray. For this one, we're going to have to create a new array that's sized to be able to store however many items we have in our set. So I'm going to say var destination array equals a new object type array is what we're creating here, and it's going to be of size this.size. Once I have that array made, I'm going to go ahead and iterate over my chain of nodes to copy their values into the array. I'm going to need not only just a current node variable to keep track of my position, I'm also going to need to have an index since I'm going to be writing into the array. So I'm creating this field here that I'm just calling IDX, and I'm saying equal to 0. I'm also going to go ahead and do var current node equals this.head node. And I'm going to loop while current node is not null, which means that we're still on an active node inside of our chain here. And just as a safety measure, I'm also going to go through and add a second condition that IDX is less than destination array dot length. This will ensure that I don't end up with an index out of bounds exception, although I shouldn't actually get that anyhow, assuming that I've coded everything correctly. And I don't have anything weird going on with like threads where multiple changes are happening at the same time. Inside of this while loop here, what we're going to do is go and store the value of our current node in our destination array. So I'm going to say destination array sub IDX equals current node dot get data. So we'll take the item from the first node and put it in the first array element, which is going to be element 0. Once we've gone and stored things, we want to go ahead and increment our counter. So I'll do IDX++, and we're also going to go and move to our next node. So we'll say current node equals current node.get next node. Eventually, we'll get to the case where we run out of nodes and current node will be null. That will trip us to get out of the while loop. That should happen at the same time as IDX becomes equal to our destination array length. Bear in mind that since arrays are 0 indexed, the last valid index is going to be the size or length, in this case here, of our array -1. Once we've gotten out of the loop, that means that we've populated all our values, so we'll go ahead and return destination array. So that we can see how we would work with a set, I went and created a new project here in Eclipse, and I added the other projects to the Java build path. And you can see that I've started to stub out a main class. Let's go ahead and create a new set here. And so I want to go and specify my variable as being of the interface type. So let's go ahead and say set interface, and we'll go ahead and store some strings. And I'm going to go and call this variable set, and I'm going to set equal to a new linked set that is storing strings. I'll need to go and import set interface and linked set. I'll use the quick fixes here in Eclipse to go ahead and handle that. Once I've got the set, I can go ahead and place some items in it. So let's go and add different WVU cities. So we'll do set.add, and we'll add Morgantown. We'll add Kaiser. We'll add Beckley. And then let's go ahead and try to add Morgantown a second time. We'll go ahead and print out the number of items in our set. I'll just do a printf statement for this. We'll say there are %d, that's formatting string for an integer, cities in the set. We'll do a new line at the end, and we're going to say here we're going to do set.size as the value there. And then we'll go ahead and get and print the contents of the set. So we'll say var cities equals set.toArray, and then we'll just go and iterate over that array to print things. I'll do a for each style loop here. We're going to say var city in cities, and we'll just call system.out.println for city. When I go ahead and run this code, you'll see that I get that there are 3 cities in the set: Beckley, Kaiser, and Morgantown. That's what we expect. Since sets can't have duplicate items, even though we've tried to add Morgantown to it twice, Morgantown should only appear once in the set, because on the attempt to add the second item here, it would have seen that it was already contained and it would have returned false from this method. So it looks like things are in good shape. For this lecture's participation project, I want you to start off by downloading the starter code that is provided in eCampus. It's based off of the linked set that we have gone and implemented here as part of this lecture. I want you to modify the linked set class to go and throw an illegal argument exception if we try to add a duplicate item to our set. I want you to also go and modify the main class, and there's 2 things you need to handle. One of them is that you're going to have to catch illegal argument exception if it gets thrown, and in that case I want you to go and display an error message. But I'd like you to avoid having that exception be thrown in the first place. I want you to go ahead and do some checks to go and prevent the situations that will result in illegal argument exception from being thrown at all. When you turn in this code, you should go and submit both your updated linked set and main classes. That's where we're going to end things for our look at sets and exceptions. If you have any questions, join the Q&A session or send me an email. Thanks, and have a great day.